Before the atomic theory we know of today, ancient Greek philosophers attempted to understand the fundamental constituents of the physical world. Thales, an ancient Greek philosopher, is often credited as one of the first philosophers to seek naturalistic explanations for the origin and nature of the universe, moving away from mythological and religious accounts. He proposed a cosmological theory known as the element theory, in which he believed that all things are made up of water. Following the steps of Thales, Anaximenes also proposed a theory which can be summarized as the doctrine of air, where he posited that air was the arche in which all things originated and to which they return. Another theory is that fire is the element of which everything originated. This is the theory of Heraclitus, where he regarded fire to be not just a physical element, but as a symbol of dynamic energy and transformation. These theories involving only one element, however, does not satisfactorily explain the complexity of the material world. Empedocles introduced the multi-element theory. This theory proposed that all matter was composed of four elemental substances: earth, air, fire, and water. Each element was associated with certain qualities and properties, and changes in matter were thought to result from the combination, separation, or transformation of these basic elements. While this non-atomistic theory has been largely superseded by modern scientific understanding, it still played a crucial role in laying the groundwork for later scientific inquiry and study of chemistry and physics.
The atomistic theory, which is a theory that things were made up of atoms, was first introduced by Greek philosopher Leucippus and his student, which is widely regarded to as the Latin philosopher Democritus. The term atom was derived from the Greek word atomos, meaning indivisible. Democritus' theory that things are comprised of atoms, which were thought to be unchangeable, indestructible, and have always existed, as well as the void, which are the spaces in which the atoms moved in, better explain how things are and how reality works. However, Aristotle opposed this idea as he had believed in the multi-element theory, which, which suggested that everything was composed of four primary elements, namely earth, air, fire, and water. Despite the fact that atomistic theory did better explain how things are, Aristotle being more influential meant that his idea prevailed, thereby overshadowing the theory of atoms. This would then be left unexplored for centuries until a scientist named John Dalton came along and reintroduced the idea. A major contributor to Dalton's hypothesis was Antoine Lavoisier's law of conservation of mass, stating that the mass of a closed system of substances, regardless of the processes acting inside the system, remain constant. This, to Dalton, led to the idea of the existence of chemical elements which made up everything, and that matter cannot be created nor destroyed, only change from one form to another, implying that for a given chemical process, the mass of the product of a reaction must be equal to that of the mass of the reactants. The reduction of the idea of chemical elements then led to Joseph Proust's law of definite proportions. This entails that pure substances will always contain the exact proportion of its constituent elements by mass. This was then questioned by another French chemist, Claude Louis Berthollet, arguing that elements can combine in any proportion. Following this thought, again, John Dalton arrives to the law of multiple proportion under close analysis of Proust's law of definite proportions. He noticed that if two elements form more than one compound between them, then the ratios of the masses of two elements will be in ratios of small numbers. Dalton then argued that the assumption that the elements were made up of substances that were the same type of as that of the atom, which are indivisible, would explain the law of multiple proportions leading to what is now known today, Dalton's atomic theory.
A groundbreaking framework that helped us in understanding the nature of matter. In his first theory, Dalton proposed that all matter is not continuous but composed of indivisible particles known as atoms. These atoms were considered the fundamental building blocks of all substances. Dalton postulated that the atoms of a particular element are identical in their characteristics such as sizes, masses, and chemical properties. However, atoms of different elements exhibit variations in these attributes. According also to Dalton, atoms are indivisible and indestructible. This concept was a departure from earlier ideas that suggested matter could be infinitely divided. One of the key principles of Dalton's theory was that atoms combine in fixed, simple, and whole number ratios to create compounds. This concept laid the foundation for understanding the stoichiometry of chemical reactions. Dalton also proposed that during chemical reactions, atoms are neither created nor destroyed. Instead, they are arranged to form different compounds, and this principle is consistent with the law of conservation of mass.
So for the subatomic particles, J.J. Thomson is the one responsible for the discovery of the electron. Discovered the electron in the cathode ray experiment. So here we have a cathode ray tube in which he actually introduced an electric current to form a cathode ray towards the center. So as he considers light, which is actually the cathode ray. So when Thomson introduces an electric or magnetic field towards the cathode ray, he actually observed that there happens to be a deflection in the cathode ray tube. So his calculations actually prove that there exists a particle that is lighter than the atom itself, and he actually named it as corpuscles or corpuscles, which we later rename as electrons. A model. So this model is actually called a plum pudding model. So plum pudding, so from the word itself, this describes that the electrons is actually evenly distributed all throughout the atom itself. In this case, that the spherical cloud is a positive charge and its pudding or plums were actually electrons. However, this model is no longer accurate since we can now determine the proper area on which the electrons could be observed.
In the early 1900s, the fact that atoms contain electrons that are electrically neutral was established. However, to attain electric neutrality, an atom must contain an equal number of positive and negative charges. As a solution, J.J. Thomson proposed the so-called plum pudding model, which is an aid to the prevailing problem, which became an accepted theory for years. In 1910, physicist Ernest Rutherford decided to use alpha particles to prove the structure of atoms. Rutherford carried experiments using thin gold foils as target of the alpha particles from a radioactive source. They observed that the majority of the particles penetrated the foil either undeflected or with only a slight deflection. But every now and then, alpha particles are scattered at a large angle. In some instances, an alpha particle bounced back at the same direction where it came. Based on his observations regarding the experiment, Rutherford inferred that most atoms must be an empty space, which explains why majority of the alpha particles pass through the gold foil with little to no deflection. He then proposed that the atom's positive charges are all concentrated in the nucleus, which is a dense central core within the atom. The positively charged particles in the nucleus are then called protons. In separate experiments, it is found that protons have the same quantity of charge with that of an electron, and it has a mass of 1.67262 times 10 raised to the negative 24 grams. And that's all for our group's discussion about historical development of atomic theory. Thank you for listening.